Hey, welcome to EarthSky. It is Monday, so that means it's time for a live interview with a scientist who has just presented us with some amazing new research. So, good morning, good afternoon, good evening, wherever you are on the planet. I hope you're enjoying the solstice, the Paris solstice part of our calendar. So, winter or summer, as the case may be. But today, Burkhard Militzer, welcome, Burkhard. Excuse me, I just thumped that microphone well. How are you today, Burkhard?
Hello, very well, thank you. Thanks for having me.
Oh, it's a pleasure to have you here. Dr. Militzer is a professor at UC Berkeley, University of California, and his research centers on exploring planetary interior geology in the gas giants and right here at home in the deep mantle of the Earth, locations that are under high pressure. And his background is in theoretical condensed matter physics. So things that are solid, which is ironic because today we're going to be talking about liquids. We're talking about liquids because your new paper, which hasn't been out very long, it comes to what I think is a pretty stunning conclusion. Uranus and Neptune, the outer gas giant worlds, might have a secret. They might have oceans. Is that right? Is that right? Tell us. I'm astounded, Burkhard. I'm speechless.
I think the ocean concept is not too novel. Actually, the reason is we always called them ice giants.
Mm-hmm.
So there was the assumption there was a lot of ice when they formed. And then as the planet formed, it got bigger and bigger. Every bolide or any icy planetesimal that arrived had so much energy that they became very hot. Mm-hmm. So all these planets, including our own, is still very hot on the interior.
Right.
So since everybody assumed the ice giants, ice was delivered, we are not the first one to say that there's an ocean in those planets. So I think that's not first. What the first one we're saying now is why the magnetic field is so weird.
Oh, okay. But the picture that I got, the one we used for this live stream, looks like a jawbreaker, a big gigantic candy. And underneath the gas is an ocean of water.
Yes.
Just regular old water.
We see
that's a novel concept, right?
Yeah, so all the spacecraft, all telescope observations, they see the atmosphere of those planets, and that's hydrogen and helium with a little bit of methane that makes it a nice blue color. But if you think that this would go all the way to the center of the planet, that the density or the mass does not work out. There has to be something else there, and it cannot be rock. So in between, rock would be too dense, and hydrogen and helium would be not dense enough. So therefore, people assume ice is a good candidate, and then they look outside in the solar system at comets and everything that swirls around still, and there are many icy objects. So the natural conclusion is that a lot of those were around when the solar system formed, and they made these planets, Uranus and Neptune. We call them ice giants just because there was ice that was incorporated in huge quantities when they formed.
Okay. And so there was an old model that there was water there, but did we think they were ocean worlds, that they had actual standing bodies? Well, these aren't exactly standing bodies, though. What is the interior of one of these ice giants look like, according to your model?
So we
and
changed
what
it a
did
little
we
bit.
used to think it looked like?
So we got credit for saying, we say they're oceans, but in fact, we're not the first ones to say oceans.
No, okay.
What we're basically saying is there are two liquid layers. So there's an ocean layer that overlays another layer, and the ocean layer makes this weird magnetic field, but there's another layer below. And that's sort of the telltale signs. The problem with planetary science is you cannot directly send a probe down there. And we can't even drill in our own planet because it's just the pressures are enormous and it's technically impossible. So for our planet, we rely on earthquakes to tell us what's going on. And then for these other planets in the solar system, we once in a while have a spacecraft that flies there and makes measurements.
Okay, so This relates back, though, to the magnetic fields that surround these worlds, and they aren't what we expected. Is that right?
That was the triggering point for the
O-
study we are now
Okay.
presenting,
So
and that puzzled everybody.
that puzzled everyone. And so if we have, let me back up. You're describing a layer. So at the center of these ice giants is a rocky inner core that is still hot and active. Yes.
Yes, yes.
And then outside we have a layer of volatiles. Is that correct?
You could call it that. We
You
say
could
it's
call
a mixture. You call it a soup, whatever you like to imagine.
Okay.
We claim it's mostly carbon and nitrogen and hydrogen.
Okay. Carbon, nitrogen, and hydrogen. Then on top of that, and those are in the form of anhydrous ammonia and what was the other substance that was mentioned in the paper that's escaping?
You could think of that way, but that implies that they're really well-defined molecules, while these pressures are so extreme that you're breaking these molecular bonds. It's really like a soup. That's what you're simulating also on the computer.
Oh.
There are no stable chemical bonds at these extreme conditions. So they form and they disform. It's like, just like a dense system where you have no stable bonds. It's very hot, for example. Yeah.
So a lot of nitrogen, hydrogen, these are things that are used by life frequently here on Earth. And then we have this magnetic field that's generated by a rotating shell of water. Is that what's going on?
Yes. So for making a magnetic field, all you need is some kind of a fluid that moves. So what moves the fluid in the liquid outer core of our planet? So we have a very happy dipolar magnetic field. We have a North Pole and South Pole.
Mm-hmm.
And that's all driven by the iron that moves in the outer core of our planet. We have a frozen inner core, it's frozen iron, and it's surrounded by hot liquid iron. And that moves because it's being cooled gradually. And that motion of that conducting iron will actually spontaneously make a magnetic field.
It's a dynamo. It's generating an electric field. Correct?
Exactly. So we call this the dynamo process, and it's relatively well understood, even though we have never drilled to the core. It's impossible. We rely on observations, and we rely on computer modeling to understand this better.
And the models represent the observations extremely well. They match, and the predictions that the models make, we can observe we can verify those through additional observation. And we've done that. And so that's essentially what you're doing for the icy gas giants, is you have modeled these. And so this is a model that fits well, correct?
Well, I wouldn't say this is not the only model. There will probably be more models being constructed. So I would rather not claim we are the ultimate study of this process. It's an ongoing research, and we know very little. We had one spacecraft that flew by.
Right.
This was Voyager 2, and it went there in 1986. So if you think back what you're doing in 86, I was in high school in 86.
I was just graduated.
Yeah, so well, we can talk about age if you want to, but let's just move. What actually happened? They measured the magnetic field of those planets is weird. It didn't have a well-defined north and south pole. It had like little north and south poles all over. We call this disorganized, or the scientists call it non-dipolar, because it's missing this dipole moment. And that was weird. People said, what's going on here? And the first idea was basically, is it just flipping? Because the Earth flipped every so often, every 3 times 100,000 years. Would we just arrive there when it's flipping? And then the Voyager spacecraft flew to Neptune, and they found the same weird field. And they said, well, no. That just can't be just accidentally just flipping. No. It must be something intrinsic about those planets. And that was not understood. So ice giants are different. So if you think about Earth, Jupiter, and Saturn, they all have this very strong dipolar magnetic field. And Uranus and Neptune, the ice giants, are just different. And that was not understood.
No, it was not understood. So, and especially on Mars, where you have a hybrid magnetic field that's both where we don't understand. We we did a video on that, folks. So if you're interested in the hybrid magnetic field of Mars, you can go back and take a look in our archive and you'll find that. And you'll also find that we do this every week. I think we're skipping next week for the holiday. Don't quote me on that. Check, like, subscribe, and take a look at our calendar. This Friday, we will have the Sun News with C. Alex Young, who is a heliophysicist at Goddard, and he is with us every week, and he sits down with Deborah Bird for that, and that'll be at 18:15 Universal Time, which is 12:15 p.m. Central Time, and that's our normal go time. And we will also be back on Thursday to talk about the winter solstice and the Star of Bethlehem, and the New Year's Eve star. So that'll be fun. We'll have some expert sky watching advice. Back to the topic at hand. So we have an explanation here for an unusual magnetic field that we find in an ice giant. And it's caused by what appears to be a layer, possibly. Is it pure water?
We think there's probably hydrogen mixed in as well. But what we assume, so the struggle was, what is this layer? There was a study done at Harvard by our colleagues, Sabine Stanley and Jeremy Block, some good colleagues of ours, and they said, we can make this weird field, but it has to be primarily generated in a rather thin layer. And then people didn't know why would there be a layer or what would be below. And our study, actually the computer simulations that we did, showed if you started with methane and ammonia and water, and you have a mixture, this is now all done on a computer. The computer simulation showed that they separate into two separate layers. And then once we saw there's a water-rich layer, there's some hydrogen mixed in, and then there is the other nuclei, the leftover, the carbon, nitrogen, and hydrogen, they go below. That at the present time is the most plausible explanation. But like anything in science, if we go there with another spacecraft, we may get more data and we may change this. But this is at least a plausible way to interpret why are those magnetic fields as weird as they appear to be. They're basically produced in this convecting water layer and not below.
How thick is the water layer?
So this is, if you think of an ocean, that is probably not the best description. Because an ocean, it's like 10,000 meters. This is like 6 miles.
Yes.
Compared to the diameter of our planet, which is like 6,000 kilometers, the ocean is nothing. It's just a thin little thing on top, but it doesn't really add a whole lot to the mass of the planet. Now, if we go to Uranus and Neptune, it's very different. This is 10,000 kilometers. So it's basically, it's 10 kilometers here. It's like a little icing on top of our planet. There is a big fraction of the planet. So it's 10,000 kilometers. It's like 40% of the mass of the planet. So it's gigantic.
My goodness. And is there ice as well, or is it all in a liquid state?
It's too hot for ice to form.
It's too hot for ice.
The planet has maintained so much heat in the interior, and it has, the solar system is 4.5 billion years old, and the planet had not enough time to cool. So all the planetary interiors are still very hot. It's like 6,000 degrees in the center of our planet, and it's even hotter in Uranus and Neptune because they're just giant planets. Larger. And it takes them a long time to cool, and they're hot, and therefore there is no solid ice. But the atoms are there, and it's molecular or it's dissociated, but the atoms are all there, but it's too hot for anything to crystallize.
You're not an astrobiologist, but
no, I'm definitely not. No,
definitely
I think
not.
I have an opinion on some of these things, but I think that would be a mischaracterization.
That's what I want, is an opinion here. We have a water layer that's fairly pure, and it sits unmixed above what we find at the components, the building blocks of life, or could be constructed from that. and it's nice and warm. So it's got water, it's got the universal solvent that we use here as the basis for life. It's got all the nutrients and building blocks of life, and it's warm. Could there be life on these misnamed icy giants?
There could potentially, but I'm a
Potentially.
skeptic. I would like to be convinced. So I give you the
Beautiful.
positive and the negative at the same time. So the
Wow.
positive things are all the chemical elements, including water, all the building blocks of life, they're there in massive quantities. And we also have energy sufficient, but the challenge is now twofold. A, would you want to look for Uranus and Neptune to look for life, or would you actually go somewhere else to look for life? And even if you don't look, would you actually think there is likely that there's life, or are there other places where it's more likely? So that is sort of the question, like more likely. For example, we have this hydrogen layer on top that's relatively thick.
Right.
So you have to go to a rather high pressure of like 50,000 atmospheres. 50,000. So this is like on Earth, if you go to the bottom of the ocean, you have 1,000 atmospheres. So in these giant planets, before you even get to the water, it's 50,000. And then the other thing, which may be less likely, it's hot there. As you descend, it gets hot quite quickly, and it's like 1,000 Kelvin. You know, this is like 1,500 Fahrenheit. It's not the first place I would look for life.
No, it's not. But we look at places like that at the very depths of Earth's ocean, and we find smoking vents active, pumping out the nutrients, and we find abundant life. We find the extremophiles. It's possible, isn't it, that we might find something like that. Some, we're not talking about sentient octopi, octopuses, octopodes, depends on your preference. We're talking about maybe something bacterial, or it's been around as long as Earth has. We could find anything, maybe.
Sure. But if you ask me, and you have one spacecraft to send, and the two of us have to figure out where would we go, we would come up with a list of places to go. And maybe Uranus and Neptune would probably rank number 3 on this list. There would be other objects where we would go earlier, before we just have one spacecraft to send. Why don't we go to an icy moon, for example? Then we have ice there, we know that. And we know there are more modest temperatures. And on top of so you could go to Titan, for example, or Europa. But if you ask me where I would actually go, I would go to Enceladus and land.
And what would you hope to find on Enceladus? And where is Enceladus? Tell people what Enceladus is.
So Enceladus is one of Saturn's moons, and it was visited by the Cassini spacecraft. And it's very special because on the south polar region, it has an area called tiger stripes.
Called what?
They're called tiger stripes.
Tiger stripes. Okay.
Yes, and that's of course why imaginative colleagues named it that. And the reason is, if you look in infrared light, it has a striped signature. And that's because there's some bands that are a little hotter than the other one, and you have areas where it erupts. So there are geysers on Enceladus, and they bring up liquid from the interior, and it erupts for you. So you get two things with one stone, if you like. We know there's an ocean on Enceladus hidden under the ice where life could be.
Right.
But then the challenge is, if you land on the ice, you have to drill through 10 kilometers of ice to detect life. That's tough. But Enceladus erupts for you. All you have to go there to hold your hand open and collect the water and see if there's any biosignature. That's where you should really go.
Okay, so the data is just falling out of the sky there, and we need to get to Enceladus, the moon of Saturn, lickety split. If you had one rocket, you get one mission, that's where you're taking it. And what are you going to be looking for in that spume of interior liquid water. Is it water? What are you hoping it's what's it? I'm sure we've looked through it with maybe a spectrograph. What do we know about that so far?
Yes, so we did actually, the Cassini spacecraft had a simple spectrograph and it flew past and it took this iconic image where actually it turned around, looked back at Enceladus, and that was actually the sunlight streaming towards the spacecraft, and it went through this erupting geyser, and there's this big plume, and there's this colorful ionic image. But the spectrograph was not very sensitive. So it detected water and some simple, I think, CO2, but didn't detect any signature of life. So I would go back there with a really modern spectrograph and look for complex molecules, because this is our best shot to find life in the solar system, in my personal opinion.
Well, let's get back to Uranus and Neptune. Have we seen anything similar, any eruptions or any sign that anything is escaping, or is it so tightly bound that nothing can get through? Is there any similar condition there? Any way we can get into that water layer without having to go through all of that pressure that you described?
I think the gravity on these planets is very high. So there's nothing that escapes. So we will go back to those planets. So NASA has decided we're going to go to Uranus. There will be an orbiting mission. And then in addition, they will drop a probe into it, and they will sample the upper atmosphere. And they most likely will find hydrogen and helium and methane and probably other smaller species, and will tell us more what were the constituents that formed this planet, because they left a trace in the atmosphere.
Right. And so there's the lighter elements that may have come up. That's what we'll expect to find on the highest strata of the atmosphere. With how deep will they go? How far into that atmosphere do they intend to dip?
So we don't know. Scientists will design this mission as we speak. So I'm not personally doing this, but I can give you the analogy what happened to Jupiter. So there was the Galileo probe that was dropped into the planet. And it's just imagine you are sending something down that's relatively inexpensive. It cannot slow down.
No.
So what you have to do for simplicity, you have a heat shield, but the Galileo probe got hot very quickly. It went to a pressure of about 20 bars, and at that time it got so hot it stopped functioning. So we sampled the upper part of Jupiter's atmosphere, about 22 bars, and then we lost all communication. That was unfortunate. We wanted more. We want to know how much water there is. And it got us this puzzling result that it doesn't find as much water as people has hoped. And people debated it ever since this measurement was made. We will do the same thing. We hopefully have a better heat shield, and it may get us from 22 bars, maybe to 50 bars. But it's not going to get us to 50,000 bars. It gets super hot, and we cannot cool it. We cannot cool the spacecraft, the entry probe. So therefore, we rely on good luck, and hopefully will not overheat that rapidly, and hopefully get precious data that we can confirm or debunk what I just said. It could all be wrong. The measurements tells theorists, gives new puzzles. Sometimes we're right, sometimes we're wrong, but we'll get new data.
That's the exciting part of this adventure, isn't it? Is you get to find out, am I right? Am I wrong? And if you're wrong, you get to start all over and re-theorize and look again. And so they give you another mission and you go. We also dropped the Huygens probe into, was it Saturn, correct? Did we see anything?
The Huygens probe, ironically, was dropped onto Titan.
Titan, correct. I'm sorry.
So there was no probe dropped into the planet Saturn itself, but people really wanted to know what happens on Titan, because Titan has an atmosphere, has a hazy atmosphere. So that's confusing because you can't look through.
No.
So the Cassini spacecraft actually gave us remarkable insight into planet Titan, and the Huygens probe was rotating as it was descending and took a panoramic view, and they found rivers on Titan, which we've never seen before. And it found lakes on Titan. And then it landed. And then it measured the temperature on Titan. And nearby, it found things that looked like rocks, like things you could pick up, like whatever, like 5-6 inches in diameter. And it looked like rocks. And when you have something round, you think like, what made it round? And then the standard theory is it was transported in a river. And in the process, it was ground up, and the edges were rounded. Any pebble you up in some stream is round because it has been rounded ever since. So that is as far the analogy goes. And now I'll tell you what's different. So we have lakes, we have rivers, but the rocks are not made of rocky material.
No. What are they made of?
And the fluid that moves the rocks, quote unquote, cannot be water. It's too cold. Water freezes at these conditions, and what flows there are hydrocarbons like ethane, whatever you go to the gas station with. This is still flowing on Titan, and we have sort of it's a hydrocarbon mixture. And what the rocks are actually H2O. The rocks are frozen ice. So whatever moves the material on our planet, that's the water that is frozen, and the hydrocarbons are basically moving the water rocks, if you like. So what the Huygens boys looked at were actually pieces of ice that were happily rounded, and the simple analogy is that hydrocarbons actually move those around. So whenever you go somewhere new, you find something amazing.
There are so many different pathways for water to take, apparently. It really is a universal substance. This is just amazing stuff. Absolutely amazing. So we've got a probe headed to Uranus, and what will that tell us? Where do you go from here? Are you going to stick with this? What are you looking at now? What is your current interest?
So before I talk about my current interest, let's talk about this probe. And let's just get the time scale. Get an appreciation how things move in planetary science.
Yes.
So if you're a lab person, if you make a lab measurement, you can go next week, make another lab measurement and another one. And it moves on a weekly or yearly scale. Planetary science operates very differently. At the beginning, we already talked about these measurements that I helped reinterpret. They were made in 1986. And now we're talking about a new mission. And the estimate, the optimistic estimate, it gets there at 2040. And the less optimistic estimate gets at 2054. So I will not be the person who's the primary interpreter of these new data. I will be retired by the time. I will go to meetings and look at the young people who are now being trained, and they will make these discoveries and measurements. And they will look at me, and maybe I'm going to be walking around with a cane. Oh, yeah, you're the old guy who basically predicted this water layer there. And yes, I will be the old guy at that moment. So what I have some hint right now is what type of spacecraft they're going to put together now. Because these discussions are happening now.
Okay.
And it's the challenge because you need, you have a certain constraint on mass, how much payload you can actually put on a rocket that launches it, and how many scientific instruments we could put in. I just came back from the meeting in Washington about the American Geophysical Union, and there was one person who talked about maximum 50 kilograms of instruments you can bring on board, and 50 kilograms. And I tell you, you know what I want? I want an imaging device that can look at potentially detect the layers I proposed. And the person told me, you're looking for a Doppler imager. You know, this will be 25 kilograms, needs a huge amount of energy. And he says, you know, out of 50 kilograms, you think your preferred instruments will give half of the science payload to just you? And he looked at me, and I realized that I don't have the best cards, but I want this imager, so we can look at these oscillations of a planet, and then we'll know whether the layers I predict are there or not. But the person on the poster I did this conversation with, he looked at me and he said, well, it's probably unlikely we take that instrument. So we take what we get.
We do. We take what we can get, and we're great. We're grateful for it. We're grateful for it. Speaking of taking what we can get, we have taken up quite a bit of your time this morning, and we really thank you and the viewers for tuning in. This has been a quite eye-opening journey to the outer worlds for me. I did not know I didn't know almost all of what you taught me today. So you're a great teacher, Burkhard. I really appreciate your time. Remember, folks, go ahead and visit earthsky.org, and there you will find, among other things, cool shirts like this. Can you see it? EarthSky. And our 2025 EarthSky lunar calendar is out, suitable for framing, makes a wonderful gift. 'Tis the season. Again, thank you all. Thank you, Burkhard, for joining us. Really, really appreciate it. This has been a wonderful talk. I hope to have you back sometime. Folks, there's one Earth and one sky, EarthSky. Thanks for joining us. Appreciate it. Bye-bye.
Thank you, Dave. Bye-bye.
Thank you.
Okay, great.
Okay, we're done. Perfect. All right.